Hey guys, this is Steven from LegitTechTutorials, and welcome back to my product development series. In this series is the second video of my project in my ME-154 class for Bachelor in Mechanical Engineering at San Jose State University in San Jose, California. So we are building the Tripteron 3D printer, and if you guys checked out my first video, you would be more familiar with what that looks like. I wanted to go through this one because I'm a little bit more energized than last video, even though it's still 12 o'clock at night. Last video was super tired. So I'm just going to summarize a few things in that video, and then we're going to move on to adding a Trello for it for me and my group of 3 other people, so a group of 4, to specify all the specifications that we're going to be doing with this build, as I am the lead on the build, and what we're going out to achieve, and also what parts we have, what parts we don't have, what we're planning on doing, and how we're going to adjust that as well, and how we're going to deal with that, as well as how we're going to do the video series, while also having multiple people doing it as well. But like I said, because I'm the project lead, it's a little easier to do it on my end, rather than trying to follow all the other ones. So if you guys remember, this guy's the Tripteron, and we're following a lot of the stuff by this APSU guy. I don't know his first name, but he has done a lot of development, and you guys should go check him out. APSU on Thingiverse, and also Absuni or whatever. So right here, go onto his YouTube channel. He's a great designer as far as kinematics of different mechanisms and stuff. My teacher for ME-154 would really like him. So you go onto his YouTube, and you'll see a whole bunch of kinematic systems that I've never seen used before and implemented into 3D printers. But to me, it seems like he likes the Tripteron the most. But he has all different types of, even Cartesian, the normal, vanilla, kinematics. But he also has other, circular and polar and angular, different non-linear other kinematics that you've probably never seen before. So again, like I said, this particular one is this particular design was developed by a school, Laboratory D Robotics, pretty much. So I'm just going to talk, because I didn't really talk as much about, these are the original designers, were I believe they were university students in a research, I don't know if they were masters or whatever, but Quebec, Canada. Okay, so they're Canadian. Originally I said they were French. Yeah, I guess they're Canadian. Quebec, Canada. But I mean, most of this looks like Canada. Okay. Yeah, so go ahead and check out these guys' websites. And this is, like I said, these are one of their patents. And you go on here into publications and go to patents, and you'll find this in there. So of course, this is obviously not for commercial use. This is just for educational use. I will not be selling the designs. So you can find that there. And then of course, there's this guy which took this from, I don't think they ever actually did. Like, they did a little bit of pick and place, but I think that was it. So he's the first, APSU was the first guy to turn it into a 3D printer, put a 3D print head on it, and 3D print. And now, as far as I know, I think there's a few other people working on it, but we might possibly, I'm not quite sure, I need to do more research on it, but we might possibly be the second person / people to build a Tripteron that 3D prints. Alright, so I wanted to talk about how I 3D printed a few parts, and also to summarize again. So this is for a ME154 class, and it is a project to design a machine that uses mechanisms. And so I need a new 3D printer because I have a Colossal Delta, and I'm not too happy with Delta printers, so I'm going to stay away from Delta printers from now on unless I'm doing cylindrical objects. Which I do have a few projects that use cylindrical objects, but need a way bigger platform than that. So I'm going to stay away from that. Any sort of square projects that I'm going to print, I want a Cartesian, because it's just, they're way better, way easier to work on, and way easier to build also. And also a lot more forgiving as far as mistakes when building it, not very robust. So, luckily, I found a kind of interesting concept that also has a lot of strengths, and I decided to go with this because one of my buddies showed it to me, and I kept it on my mind, and then I took a picture of his phone, and I went through and I found to that original university, and then found this development, and I suggested it to my team. We created a proposal, submitted it to the teacher. The teacher was ecstatic about it. We got 100% of the proposal, so now we're full in it. So the idea that we're going to be doing is we're going to be converting this Colossal Delta to the Tripteron, and when we turn it into the Tripteron, we're going to use all the parts off the Colossal, and then we're going to use. Okay, so now this is what we're thinking about as far as how we're going to execute the project. We're basically going to be, we have to design our own mechanism. So for the class, we have to submit a proposal, design our own mechanism, do a kinematic analysis, do a stress analysis, and then do a and then there's another analysis I can't remember off the top of my head, but the kinematic analysis is next, the stress analysis, and then I think there's not another analysis. I think the next one is just you do a product video, or a demonstration video of your prototype, and then that's it. There might be something else, and we'll talk about that later. Anyways, so that's what we need to do. So one of the things that we want to, because we're already halfway through the semester, this has to be done by May 19th is our final, and each of these pieces are due in different portions of the semester. So we're already quite a bit in, and we don't want to have to design this mechanism twice. And what I mean by that is our final mechanism we want to be made out of 3D printed arms. So instead of these arms here, they're 3D printed. Now, a 3D printed arm will be a lot lighter and also be just as stiff. So, well, not just as stiff, it'll just be lighter and easier to, make, pretty much. And also because he has it open source, our designs will also be open source. I just want to put that out there, that we're doing this for education, again, not to infringe on the patent, and also not to, infringe on APSU's intellectual property. These files will go back into Thingiverse and hosted, and be open source for people to download one of our own spin on the Tripteron. So, however, we're going to do a very large format printer, and I don't have access to any printers that could print that large of arms, that long of arms. The only thing I have access to right now that can print that big is a Rep 2, which is 11 by 6, I believe, and can print a 12.5. Only one arm at a time at 12.5, and that's max. That is if the arm was just a line. Of course, it's got some thickness. So you're talking like 12.25 or 12 inches, and we're trying to hit a build volume of 16 by 16 by 16, 16 inches by 16 inches by 16 inches or more. So we're trying to hit that big of a print volume, so we need to have as big of the arms as possible. So if we could get away with that and just 3D print everything, that would be ideal, because I'll go over, I watched all the videos that are down here of him talking about it and him showing the machine, and I'm going to talk about a few things that I saw in there. So what I'm thinking right now is I don't really like that first video too much, so this will actually probably just replace this video, replace that first video. So we'll go back more into detail of what the Tripteron does. So the Tripteron is just a 3-point link, so we could get rid of that first video. It's a 3-point link, and it's Cartesian 1-to-1. So that means that this drive, when you drive it 1 inch, this guy goes 1 inch, and the effector goes 1 inch. So everything's 1-to-1-to-1. So you don't need any sort of, for example, on a delta, you need the arms are angular, and then XYZ coordinates are done by changing angles because all of the motors are parallel to each other on the same plane, but obviously rotated around a circle. So those, your G code is submitted to the controller in XYZ Cartesian coordinates, and then the controller has to convert on the fly from XYZ coordinates to angles to Y or Z movements on the motors, and then drive those steps. So sometimes if you're using like an AVR, like Arduino on the console or any sort of delta, Rostock or console or whatever, just like I'm doing, sometimes the data usage is, the strain on the CPU is so high that you can't even, or on the microcontroller, that you can't even use the LCD too much, the LCD with the encoder, because it's kind of like it'll flash and lag kind of, and also it's not as responsive. It takes a little while for it to come back and refresh the screen so you see what you're looking at. So it's very taxing because of those heavy calculations. And this is still actually true Cartesian, where everything is 1-to-1, and the X, the Y, and the Z are all isolated and are all on different planes. So there is no extra calculations there. You give all your G codes in XYZ coordinates, Cartesian coordinates, and all of your movements on the controller are Cartesian coordinates. So that means that your controller can just focus on doing arcs and also sending the information and controlling the screen. So the controller has to do a lot less trig and other stuff that the deltas do. So this is all linear control. So again, if you move this 1 inch, this guy moves 1 inch, this guy moves 1 inch. And it's very interesting to see it move. So let me go ahead and show you guys an example of what it looks like when you see it move. So that's kind of how the whole thing moves around. So it moves around like that, with each arm again independently driven. And each of these angles, the angles, you don't care about the angles. The angles are just interdriven by each of these different pieces. So if you move this one this way, this angle is going to change. So all the linkage does is connect these pieces and add, technically add some stuff for our class, for the mechanism design. So our teacher could say, hey, if this piece is at 5 inches here, 5-inch absolute positioning along the rail, this is at 2 inches, this is at 2 inches, what are the angles of each of these joints between these here? So something like that, for him to ask us, and also in our kinematic analysis. But with this, the idea that I like so much about the Tripteron is that it has basically the advantages of the simplicity of our Cartesian as far as the controller, and also the isolation of axes. So if you have some issues with like some banding on the y-axis, it's a y-axis problem. If you have some weird thing going on the x-axis, it's the x-axis problem. If you have something going on with the z-axis, it's the z-axis problem. All the problems are isolated. Now on the delta, all three are driving each other. If one screwed up, it's going to mess up everything else because they have to be moving in sync, right? So there you can't necessarily tell which motor is which unless you sit there and watch it, or do some sort of calibration thing where you push the motor where you have the motor go towards this tower and then figure it out from there. So here, easily just look at a part and have maybe an XYZ on top of the part, and then you'll be able to say, hey, it's on the X or the Y or on the Z very quickly. But it also has the lightweight. It also has lightweight to it compared to, similar to a delta. So it has the simplicity of a Cartesian, but the speed of a delta. So the main reason why you'd go with a delta is the high speed. And the main reason why you'd go with the Cartesian is the simplicity. So it has the best of both. But this design, not technically, because it has the aluminum here, and these add the aluminum extrusion. These add a lot of weight. So so now that if you guys want to see some more information on the Tripteron, you guys can check this out on the Thingiverse. Just type in Tripteron Thingiverse and then go to APSU's page and take a look at it. But you're gonna see a whole bunch of my series, so just don't worry about it. You'll see a whole bunch. And watching this video, you can see the issues that the extrusion have of the weight, right? So that's why we decided on our final piece, on our final machine, to have all the arms 3D printed. So with that, we can control the infill, the shape, and how solid the arms are. So we could drop a whole bunch of weight. So maybe we could print those 50% infill, 25% infill, and then drop this weight. And if we drop the weight, we have our basic equation of force equals mass times acceleration. We have a certain force that we can put out of the motor, right, max, and then if we drop the mass, we can get more acceleration. And that's just how it is. The only thing we have to watch out for is also how much bending these things do when you're throwing that momentum around and stopping the momentum and accelerating out and just driving these forces. So you don't want these things to like flex at the top of the tower, because here's where it's going to flex the most when this guy stops. And then you have to stop all this weight, and then this also with having a hot end on the bottom. So that is what we were deciding on doing, was doing all 3D printed legs here. But like I said, I don't really have access to that big of a 3D printer. I have the Rep 2, which is 11 by 6, which could do a 12.5 diagonal. If it's a straight line, we'll probably do 12 and a quarter for that thickness of arm. So we might even do that. We might even just print it. But if we can't print it, we don't have any access to any printers, then we would probably use this style design where it uses these joints, and then you just slide the aluminum extrusion in there. Now the issue with that is that, like I said, it's heavy, and number two, we don't want to design two different machines, because our final machine is going to be the 3D printed, like the 3D printed arms, because that's easier for us to analyze, and the kinematics, the stress analysis, and also the final video it would be quicker. I mean, for the final video, it could be any sort of prototype. It could be like this, but all the analysis has to be done on our design. So our design would be a lot easier and a lot quicker. We don't have to worry about, you know, how it goes into this, and then having multiple materials in one piece. Even though Fusion 360, which this will all be designed in, has all that capabilities, it's just more difficult. So we don't want to have to design two different printers, one for the prototype and then one for our analysis. So we're going to use APSU's open source project and maybe modify a few things, and then use this as our prototype. But our main changes on this guy are going to be these rails are going to come out of, we're going to move these rails to coming out of one axis. So the Z is going to stay there, but the X is going to move here, and then the Y, for example, let's just say that this was X and this is Y. The Y would move here and the X would move here, right? I'm trying to do the right hand rule, so I guess, yeah, so this would be the X, this would be the X, and this would be the Y with the right hand rule, and this is the Z. So now we could eliminate this extrusion, this piece of extrusion, this piece of extrusion, this piece, this piece, this piece. So now all you have is 1, 2, 3. 3 pieces of extrusion all around the center piece. And then we're just going to have to reinforce crap out of this and also drop a lot of this weight so this doesn't nearly have to be as strong. And then we're going to put a brace that goes across the middle here from side to side, and then our print bed's going to go on top of that, and we're just going to put gussets all over the place. But with that, we have to change, you know, the end effector. But if we're designing it with printed arms, we're pretty much going to redesign everything. And if we have the opportunity to print the arms on that particular printer, then we'll just go all out with that. Now, all right. So now we'll do what we're going to be using to convert, and also So that, and then we'll write down the features. So this is my Costal Delta, and I started this little blog on my website www.thegreenengineers.com. I was talking about converting a Costal Delta to our Cartesian, because I wasn't a big fan of the Delta, so I really wanted for a long time to convert it to a Cartesian. So this is what we have. So this guy is all made out of 2020, and it also has the linear rails that you see on this guy, linear rails and carriages, right? Now, I have really long aluminum extrusion, I have all the end stock, everything, a full built 3D printer, and it turns out that if you go here and look at the build, and this is also why I picked this project, the bill of materials are almost exactly what I have on this 3D printer. Pretty much exactly. I actually have even more on this printer than I do on this bill of materials. And as you see at the end of this bill of materials, with all the extrusions and motors and T-slots, a whole bunch of T-nuts, bearings, fender washers, all that stuff, you end up with $261, while I have everything here, which I originally bought for $330. So, that being said, quite a few pieces on this are, because it's a Delta, are way bigger than his design. Some of the pieces on here are like, my rails are like 500 millimeters, while his rails are 300 millimeters, so almost twice as big. Right, so here I have everything set up. So these three uprights are 700 millimeters, 27 inches long, and then I have 700 mil, 27 inches long, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 300 mil, which is 12 inches, aluminum extrusions for the braces. Then I have the 3 500 mil rails, one here, and then one on the tower in the back that you can't see. Yeah, and then that's pretty much it. And then I got the hot end, I got the control board, I got the Bowden extruder, I have all 3 motors, I have a 360 watt power supply, I have a circular bed, so I'm going to have to get a square bed, right, obviously. But yeah, so we have pretty much everything we need, plus a little bit more in extrusion to do this entire project. So, that being said, we have, let's go ahead and tell it the features that we're going to change. So, it's going to be, we're shooting for 16 inches by 16 inches by 16 inches. But let me go back here. However, I'm going to say note, our rails are 18 point something. I believe this is like 18 inches or so. So our rails are actually 18 inches. So that's basically what these pieces are going to be 18 inches, 18 inches, 18 inches, 18 inches. So we have a total of a maximum possibility of 18-inch print volume. So 16 by 16 by 16, and then we're going to use the three main extrusions, the Z, the X, and the Y, all out of one origin location, right? So just three main pieces of extrusion, the X, Y, and the Z, all out of one origin point, and then one diagonal, right? But we're not, because the diagonal isn't technically necessary if we could attach the bed from the other corners. Then we want, ideally we want 3D printed so the entire mechanism 3D printed. Everything except for the rails. So everything past the rails down is not 3D printed, but everything up besides the bolts and the attachments are 3D printed. And then 3D printed almost entirely in one piece. So as you see here, you know, the number of nuts and washers that you start to use just goes crazy, like 48, 69, like crazy numbers of bolts and washers. Bolts, washers, and T-nuts. So it would be really nice to get rid of most of that. So entire mechanism 3D printed. So those are the arms, basically the arms and the arms, joints, and effector. Running using Marlin. And a ramps. And I have a ramps on that one. I have a ramps 1.4 with Mega, with the ML Mega or Arduino Mega. So run using Marlin. They're using belts. So this design is using belts, and we have me and my team have a few ideas on counterweighting this belt to hold this guy up. But we're gonna get rid of a lot of the weight if it's 3D printed. Okay, using belts, entire mechanism 3D printed arms, running using Marlin and ramps with Mega using belts. Try to get a heated bed, but because that's an arbitrary size, it's just going to have to be a flat printing surface. So, I mean, other than that, obviously it's a Tripteron. But you get the idea since it's in the title. Okay, so, and then all metal hot end. Well, it's not all metal, but because it has liner in it. But yeah, basically it 3D prints. At the end of the day, it 3D prints. And also, it's a Bowden. Obviously, it's a Bowden setup. And as of right now, not heated because there's a few issues with the heated part. Alright, so that is basically what we have. So yeah, let me talk about, yesterday I printed some of those elbows, and I don't know how APFU is printing these, but some of these parts that you see here are not really designed for 3D printing without supports. Like, I don't want to spend that much money on this project where I have to use like a U-print, which I have available at the tech shop, but it's very expensive, and also the supports are very expensive, but the supports are dissolvable. So for example, if I show you here, so this one, is it this one or these other ones? There's a whole bunch of them, but this one, like for example with where's the tongue? This is the tongue. So this one, it has a hole in the top here. Let me see if I can, there we go. So it has a hole in the top here. So you can't print it with this orientation because this is floating. You can't print it with any orientation that rotating without this being floating or this being floating. And then you can't print this flat on the plate because now this top piece is floating. So you can't put your 2020 in there. So how I printed it is I printed it with this flat. Now with this flat, now you have this overhang. This is overhanging. So this should have been a 45 that way, or a 60 that way. So that's kind of one of the things, like some of these things are designed kind of funky. I mean, aesthetically it looks great, and if you have something where this top piece doesn't sag at all, or you have software like Simplify 3D, which I should definitely invest in, but I haven't yet, where that won't sag, then sure you could do it, but once it sags, you either have to file the crap out of it, sand the crap out of it to get the 2020 to fit in there, or you're gonna have to figure something else out. So with that, this was crazy, like swirly off my console over here. My console doesn't have a cooling fan, so this was crazy stringy. And then this was not that great because there's no cooling fan on it. But still, unless I have something where the supports come off very easily, this is going to be difficult to print. So that's why we were thinking of kind of, going off of this guy as, as more of a, just kind of a example, and then just kind of going with our 3D printed legs. Especially if we get the, the most of the stuff going. If we get the printer, the MakerBot, in order to get the entire legs on there. And you'll see some other stuff in here that we might also use, like this is a motor mount, and then we have some gussets which could be used as well. We have these guys, which we definitely could use. Like this one's the one that we would use, the offset one, the offset knuckle. So I mean, there are a few things that we would want to change, and then obviously the end effector is completely different on ours, because we would have one joint here. We would have one joint like back over here for the Z, and then another joint here for the X. So like another joint that would be like where that joint is, and then this joint would be sort of where it is. So also with this design, you'll have more of a front. So this diagonal here would be like a front. Here you don't really have a front. I guess this would be the front, but you have like a bar going over it. So this way you would have a front end of the printer where you could easily get in and pop your parts out. And also it would be great for like a back corner installation. So if you have a back wall, put it up against the back wall, or close to the back wall, because you do need some space for this to go. And so I think that would be very good. Also, of course, as we explained, our extrusion is going to be a lot longer. He's using 175mm extrusion for the arms, and then he's using 305mm extrusion for these base supports, while we're going to be using 500mm for this one, and then this one we're going to use 300mm. Because I do not want to cut my 2020 because I could want to use it later on in another project. And plus, at the end of this project, we're probably going to have printed arms. So right off the bat, we'd probably not even want to use the extrusion. It is too heavy. It is limiting your acceleration, your print speed, for not really that big of a gain as far as... Because that's the thing, it's like a double-edged sword. Like, if you're going too heavy, then you're adding more forces that material needs to withstand. If you go lighter, then that material needs to, and you're just all the forces you have is just the momentum, just accelerating it from a positive acceleration to a negative acceleration, and changing it to a different direction. All you have acting on it is its mass. So the lighter the material and the stronger the material and lighter the material is, the better performance you're going to get. And on this one, I was thinking maybe like some 3DX Tech carbon fiber PLA, where it's amazing in flex. So, and it's very resistant to distortion. So those are a few things that we were thinking about, and then here is like here's like a similar one. So we're gonna have something like that basically by the end of the series. Have something like that we've done a whole bunch of stress analysis on, and then eventually have a finished 3D printer. If we can't get the arms to work, which we shouldn't have an issue with on that printer, even if we're limited on the print length right now, what we could do is just we put that on the printer and then print it on that printer. So we build the Tripteron, then print it on the Tripteron. So a lot of the stuff on the Tripteron will have will be able to self-replicate, which is also another big thing for the RepRap community. And then here's one that he's built, right? Not new renderings. All right, so that is basically it. Okay, so yeah, and then let me go ahead and say what we need to do. So 3D printed minded design, what I mean by that is the arms are designed to be 3D printed, so not have any... Oh yeah, another thing I forgot to mention about this is that this radius is too intense, so when you have it flat, that radius is overhanging and it freaks out on that radius. That was another thing I forgot. So have your mind around designing it for a 3D printer. That is our manufacturing technique. So we're going to design it to where we have to use as few other filaments as support, and as few ways as possible. So design it around where we don't have to use any supports. So an entire 3D minded design, then we need to do kinematic, and then we need to build a prototype. Then we need to do the kinematics, which is next. which is coming up here soon. That's actually assigned. Then we have the stress analysis, then which is going to be all on Fusion. So Fusion stress analysis, Fusion design with some of the other guys in my group, but I'll take you guys along with me. Stress analysis, and then finally a demo video. So that's the things that we got to do, and this is the first video talking about this particular project. Alright, this is Steven from LegitTechTutorials. I'd like to thank you guys for watching this video in my new series, or new season, of the Tripteron ME154 project. So stay tuned for more videos in this series and other series as well. I'll see you guys in the next video. Thanks for watching. Take it easy. Peace.